GOO, a dataset for gaze object prediction in retail environments. Gaze, or knowing what someone is looking at, clues us in as to what a person might or may be doing. People looking at each other are likely communicating. Someone looking at a traffic light may be planning to cross the street, or a person looking at a cereal box may be considering buying it. A common scenario for gaze is for people to look at objects, if it just caught their attention or if they're interacting with the object. Needless to say, being able to identify the object being gazed at helps us in understanding a scenario. However, current gaze estimation methods focus on predicting the gaze direction and/or the gaze point in an image. Existing gaze-related datasets do not have the necessary object annotations to train methods that are able to exploit object features. In scenes with multiple objects of interest, filling this lack of object annotation presents an opportunity to further advance gaze estimation research. Inspired by how humans perform gaze following, it seems natural to take into account objects in the inferred gaze direction to confirm where and what exactly a person is looking at. Similarly, teaching a gaze system to be aware of the objects in a scene may result in more accurate predictions. To this end, we present a new task called Gaze Object Prediction, where one must infer the bounding box of the object being gazed at, referred to as the gaze object. The task is not only challenging, but also encourages the use of object features present in the scene to build better performing gaze systems. In our work, we focus on gaze objects in the retail environment, which presents promising applications in market research. To address the lack of existing datasets for our proposed task, we present a new image dataset called Gaze on Objects, or GOO, a dataset tailored for gaze object prediction in retail. The GOO dataset is split into two domains: GOO Real, which is composed of 9.5K real images, and GOO Synth, which consists of 192K synthetic images. GOO Real is a real-world mockup of a retail environment, while GOO Synth is a realistically rendered replica of GOO Real created in Unreal Engine. The environment for both consists of two shelves containing grocery items, each one of 24 different classes. A sample image consists of a human or human mesh model looking at an object on the shelf. As with existing gaze-related datasets, head bounding box, eye point, and gaze point on the object is provided. Additionally, all objects in the scene are annotated with their respective bounding box, class, and segmentation mask. With these annotations, GOO can also be used for other tasks such as object detection and segmentation. For each image in GOO Reel, there are around 80 total grocery items, each belonging to one of 24 different classes. 2 cameras are used, one facing each cabinet, and 100 human volunteers, 68 male, 32 female, ranging from 16 to 50 years old, are instructed to look at the objects. The shelves are filled up with 3 to 6 instances of the same grocery item. The procedure for data collection is as follows. A randomized list of specific objects to look at is created for each volunteer. Then, this list is used to instruct the volunteer on the item to look at. Videos are then taken of each volunteer as they gaze at a total of 24 items for a few seconds each. Lastly, for each volunteer, the items are randomly shuffled to avoid overfitting. Volunteers are also unique to either the train or the test set. The list is then used by the annotators to mark the gaze object, removing any ambiguity from the ground truth. GOO Synth forms the bulk of GOO's training data and is constructed to be a replica of GOO Real. Being programmatically generated, it has more variables that can be adjusted to diversify the data. GOO Synth uses the same 24 classes of grocery items, with the packaging of the real objects scanned to be used as textures. 50 virtual cameras are placed around the scene, and 20 human mesh models are used, highly varied with respect to skin tone, whether they're male or female, the body form, and the outfits. Other elements such as background and lighting can also be adjusted. In total, 38,400 scene environments were created. To simulate gaze, a gaze vector originating from the eyes of the model perpendicular to the face is directed towards the gaze object. Background and lighting conditions are randomized, then 2 out of the 50 cameras around the scene are randomly selected to capture an image. Similar to GOO, human mesh models are unique to either the training set or the test set. GOO, with its extensive annotation, makes it applicable to a variety of tasks. In our work, we provide baselines for GOO on the tasks of gaze following or predicting the gaze point, as well as domain adaptation. We leave performance metrics as well as evaluations on gaze object prediction to future work. To provide baselines on the GOO dataset, we carefully select gaze estimation methods based on the following criteria. First, methods should have an existing performance benchmark on the gaze follow dataset. We use this benchmark to guarantee the correctness of our implementation before evaluating on GOO. Second, the input to the network architecture should only include the full RGB image along with the head location. This criteria rules out methods that use video, preceding frames, or 3D annotations as supporting data. Lastly, output of baselines include a final gaze heat map where the point with the highest confidence value is the gaze point. Considering the above criteria, the following methods are selected as baselines to be evaluated on the GOO dataset. All of these are implemented in a unified modular code base based on the PyTorch framework on a single machine. The standard metrics for evaluating gaze following are used not only for the gaze follow dataset, but also for the GOO dataset. We consider AUC, or area under the ROC curve, L2 distance between gaze points, and angular error between gaze vectors. For domain adaptation, simple transfer learning is conducted. Models which have been trained until convergence and GOOSynth are subjected to 0-shot, 1-shot, and 5-shot training on GOO before being evaluated on its test set. Models which have not been given GOOSynth pre-training are also subjected to the same training on GOO with the two setups compared using the previously discussed metrics. We first present our benchmarks on the gaze follow dataset compared to the results in their respective papers. We attribute the largest discrepancy between our implementation of Recasens et al.'s work to ambiguity of training details in the paper, as well as the different framework used. The performance of the other two baselines are much more accurate due to the code being available online. Evaluation of these baselines on the GOOSynth dataset produces the following results. By comparing benchmarks achieved on GOOSynth compared to gaze follow, some analysis can be drawn regarding the difference in performance. Baselines achieve higher values on AUC and L2 distance on GOOSynth, which we hypothesize to be because of the singular context of retail for the GOO scenes, as opposed to varying contexts in gaze follow data, making point estimates and heat maps harder to learn. On angular error, however, baselines perform worse on the GOOSynth dataset. This is due to the samples in GOO where the human head is facing away from the camera but towards the shelves, making it hard for the models to make use of facial features to estimate direction. We follow with our results for baseline evaluation on GOO. The values consistently show that models pre-trained on the GOOSynth dataset achieve higher performance on all metrics compared to models without the synthetic pre-training. Using Chong et al.'s gaze network, we observe sample gaze point and heat map predictions shown in the following figure. After 5 epochs of training on GOO, models with GOOSynth pre-training achieve higher quality heat maps and more precise point predictions, whilst those without pre-training seem to be unable to classify background pixels, producing the blue tint. In this last sample, we can observe that the GOOSynth pre-trained model is more robust to subjects with their back and head completely turned away from the camera. In conclusion, we present Gaze on Objects, or GOO, a dataset for gaze object prediction in retail environments. We provide thorough experiments for benchmarking existing methods on our dataset, which we made available online. In the interest of domain adaptation, we also evaluate the performance of baselines on GOO given whether they receive pre-training on GOO. We hope the extensive annotations in GOO inspire future work on gaze object prediction, producing novel architectures, metrics, and training methods for gaze systems to infer a gaze object.